In this video, we're going to look at precipitation of ionic compounds. So predicting whether or not a solution will form a precipitate or not. The first thing we're going to do is define what's called our ion product. And we're going to use Ksp as the abbreviation. I actually learned it as IP for ion product, and I tend to use that sometimes also, so just do be aware that IP and Qsp are the same thing. And this is essentially what Qc was back in chapter 13. So it's set up the same way that our equilibrium constant expression would be. It's just that the concentrations don't have to be equilibrium concentrations. So set up similar to Ksp, but the concentrations do not need to be equilibrium concentrations. And I probably didn't actually make a big deal that in the original video where we started talking about Ksp, that they needed to be equilibrium concentrations. I'm assuming at this point that you know, because we're solving for an equilibrium constant, my concentrations do need to be at equilibrium. So when we're setting up our Ksp expressions, all of those concentrations are equilibrium concentrations, even if I didn't say that. Here we're going to set it up similar, so concentration of our products raised to powers equal to our coefficients over reactants. The reactant is going to be a solid, so we're going to exclude it. It's just that the concentrations don't have to be at equilibrium. So set up similar to Ksp, but the concentrations do not need to be equilibrium concentrations. So for example, looking at calcium fluoride again, I'm going to form calcium ions and 2 fluoride ions. And if we were to set those equal to a Ksp, it's going to be the concentration of calcium at equilibrium, right, multiplied by my concentration of fluoride ions raised to the second power, also at equilibrium. If I use Qsp, I almost wrote IP there, very, very similar. It's just that these don't have to be at equilibrium. So I'm going to put a T here just for any time, right? It doesn't have to be at equilibrium, but at any point during the reaction. Fluoride, again, squared, because I have 2 moles, right, raised to a power equal to the coefficient. But again, at any time during the chemical reaction, right, it doesn't have to be when the rate in the forward and the reverse directions are equal. And then what we can do is we can compare our Qsp to our IP to see which way our reaction is going to shift, right? Anything that's going to shift it towards the reactant side, right, that's my solid, I'm going to form a precipitate. Remember, precipitate is a solid that falls out of solution. So if I have a solution and I shift it towards the solid, I'm going to get a precipitate. If I shift it towards the aqueous ions, towards my products, I am not going to get a precipitate. So if my Qsp is greater than Ksp, and remember we want to get to equilibrium, so our value for Ksp is our goal. So if my Qsp is too large, right, I have a greater than sign, so this is too big, that means I have too much of this, I need to decrease it. The way to do that is to go towards my solid, so I will form a precipitate. So the solution, we could say, is supersaturated, and a precipitate will form. right? We could say the reaction shifts towards reactants, which is the solid. So if my ion product constant, right, is bigger than my solubility product constant, I will form a precipitate. And then the opposite, if it's smaller, right, again, the goal is to get to equilibrium. So if it's smaller, I don't have enough of this, right? I need more, I need to increase it. To do that, I'm going to shift towards my ions because I need more of them, and I will not get a precipitate. So the solution is unsaturated and a precipitate will not form. Right? Our reaction shifts towards products. And then if they're equal, we are at equilibrium, right? If Qsp is equal to Ksp, my reaction is saturated, or my solution is saturated. Remember, these values are measured, right? Our values for our solubility product constant, Ksp, are measured when our solution is saturated. So our solution is saturated and precipitation will not occur. Right, we are at equilibrium. And no shift occurs. Remember equilibrium is dynamic, right? Both the forward and reverse direction are occurring. So when we say no shift, I'm still forming products, I'm still forming reactants. We just happen to be forming them at the same rate. So I do have an example for us. So we want to know, will a precipitate form when 150.0 milliliters of a 0.75 molar zinc nitrate solution is mixed with 250 milliliters of a 1.50 molar sodium carbonate solution. We do need to calculate IP or Qsp, our ion product constant, and compare it to Ksp, our solubility product constant. Before we can do that though, what we need to do is write our ionic equation, look at both of the products from that equation and see which one is going to potentially be our precipitate, which one is insoluble. And if you need to write the whole ionic equation, cross out your spectator ions to be able to figure it out, go for it. I'm going to kind of do this a shortcut way. So I know that zinc nitrate is going to separate into zinc ions and nitrate ions, right? Over here I have sodium ions and carbonate ions. And there would be 2 sodium, there would be 2 nitrate. I don't really care about that right now. I just care about what the ions are. So I know when I take these 2 solutions, and both of these are soluble, so they would split into ions like this, I'm going to have a double replacement reaction. So what's going to happen is this sodium is going to combine with this nitrate. I'm going to form sodium nitrate. you would look at your solubility rules. Sodium nitrate is soluble, so these would be aqueous. On the product side then, I would also write them as sodium ions and nitrate ions, and they're actually just going to get canceled out. I know that this zinc is going to combine with this carbonate to form zinc carbonate. Looking at the solubility rules, that is a solid. I would keep it as zinc carbonate. So the balanced equilibrium equation that we care about for this reaction is going to be zinc carbonate solid dissociating slightly into zinc ions plus carbonate ions. And again, if you need to write the entire equation, cancel out your spectator ions to be able to see that, go for it. I'm just hoping at this point you can kind of jump right to this part without having to do that extra work. But again, if you need to do the extra work, by all means do it. I know that my ion product constant then is going to be the concentration of zinc ions raised to the first power, because there's 1 mole, multiplied by my concentration of carbonate ions, also raised to the power of 1 because there's 1 mole. So we need to calculate that and then compare it to Ksp, which I should probably give us. Ksp for this problem is 1.2 times 10 to the negative 10th. Once we do that, we can tell whether or not a precipitate is going to form. So I do need to calculate those concentrations. And I'm just going to take these numbers from the problem and just write them down below here so I have everything kind of in one spot. So for zinc nitrate, I had 150 milliliters and it was 0.75 molar. And then for sodium carbonate, I have 250 milliliters and it's 1.50 molar. So we don't really care about the nitrate again. We don't care about the sodium. I know, looking at my equation here, or my chemical formula, right, there's 1 zinc and there's 2 nitrates. So I know whatever my concentration of zinc nitrate is going to be my concentration of zinc ions, right? Because there's 1 of them, right? There's 1 zinc. So once I figure out my concentration of this, that is going to be my concentration of this. If for some reason zinc wasn't the part of this compound that I cared about and nitrate was, once I figured out the concentration of zinc nitrate, then my concentration of nitrate would be twice that, right? Because of this 2. So here we do need to pay attention to those coefficients. Here I have 2 sodium and then I have 1 carbonate. So once I figure out the concentration of sodium carbonate, that is going to be my concentration of carbonate because it's a 1-to-1 ratio. Again, if it was the sodium that we actually cared about, once I figured out this concentration, sodium would be twice that because of that 2. So again, do pay attention to those subscripts. I might have said coefficients a minute ago. So what I'm going to do is I'm going to figure out the number of moles of zinc. I'm going to divide it by my total volume to get its concentration, right? Because we're mixing these. That's the other key here, right? They're mixed. So this just isn't the concentration, right? I'm taking 150 milliliters of this, and then I'm adding another 250 milliliters to it. And then for my carbonate ions, right, I'm taking 250 milliliters of this, and I'm adding 100 or 150 more milliliters to it. So I need to figure out the moles of each divided by the total volume, similar to how we were calculating concentrations when we were doing titration problems. And I'm going to use millimoles just like I did then. So for zinc, and I don't have to worry again because there's 1 zinc for every 1 zinc nitrate. I don't have to worry about multiplying it by 2 or anything. So I have 150 milliliters. And again, I'm going to use that capital M as millimoles per milliliter. And I'm grabbing my calculator. And I get 112.5. I do just want 2 significant digits, but I'm going to round when I'm done. millimoles. And then we need to divide that by the total volume, which is going to be the 150 milliliters plus the 250 milliliters. So 400.0 milliliters. And I get 0.28 molar. So that's going to be my concentration. We should put those brackets around there. My concentration for zinc. So again, I just took its volume, its concentration, multiplied them, milliliters cancel, and then that got millimoles. I divided that number of millimoles by my total volume in milliliters to get back to molarity. For carbonate ions, I'm going to take the 250 milliliters multiplied by its concentration. Again, I'm using that capital M as millimoles per milliliter. Milliliters are going to cancel. And I get 375 millimoles. And we're going to divide that by our total volume. And I get 0.938 molar. 3 significant digits for this one. So then those are the numbers that we're going to plug into our expression. So my ion product is going to equal, oops, sorry, I was going to get in the habit of starting to use Ksp. I knew that was going to happen. It's fine if you want to keep it IP, you don't need to change it. And that's going to be my concentration of zinc raised to the first power multiplied by my concentration of carbonate ions, also raised to the first power. I did drop units because I don't need to show them. Just look at our equilibrium constants for values for Q. You don't need to include them. So I'm typing this into my calculator and I get 0.26. So if we go up here, oops, sorry, I went way too far. I'm just going to copy this number down. Right? Comparing these two, Ksp is much, much greater than Ksp, right? So this number is too big, which means I have, we go back up to the equation, right? It's too big, which means I have too much of this, right? So I'm going to shift towards reactants, so I will get a precipitate.